是新的吧？哈，今年有发生新。
这个是不是要换那个另外一个模式，要不然他们直接投影发这个。
对，挺的。都弄上去了。
对，都弄上来，要不要重点？怕这样。OK。
new section. We are talking about distributed file systems. Okay. First, we will say something about what is a file. Okay. In general, file is an object, named object, okay, and usually used to contain, to store some permanent information you will try to maintain. Okay, and the purpose for the file usually is that when you create a file to maintain the data or information, the system will maintain the content of the file until it is explicitly destroyed. Okay. A file usually has following means or purpose, okay, created. First is permanent storage for the information, and in general they are stored in disk or any non-volatile storages or storage media. Okay. And the file not only contain the data information you like to store, usually they will contain some metadata associated with the content itself. Okay. Okay, the echo is data usually contains a sequence of items. Okay, and depends on the implementation or the file system supported. Some system may support record-based, so an item may be a record. But in general, most of modern file systems, the item just a byte, okay, just a sequence of bytes. Okay. And the metadata contain information such as the length or the size, and timestamp or types or ownerships and access control information about the particular file. Okay. The purpose for the file, another purpose is for sharing of the information. Okay. Okay. Better. Okay. So usually a file may be created by some particular user or application, and then it can be accessed or shared by other applications later. Okay. So that's another purpose for the files. And the file system it usually is a part of an operating system. Okay. And it is responsible for organize and maintain or provide this mechanism to retrieve or name or sharing of the files. Okay. And also, of course, they need to this maintenance or access need to be in authorized way. Okay. So the permission or the access control requirement specified by the owner of the file need to be enforced by the file system. And the file system usually will provide the file application interface to in such a way that the programmer can use this API to access the content of the file or the attribute or the metadata of the file without knowing the detail of this storage devices. Okay. And also, so the APIs for these file systems usually they provide this mechanism for create, name, and delete files. File name usually in most current system or modern system, usually a file name is a sequence of component names. Okay, that means and each component corresponding to hierarchy or directory structures. Okay. So in the sense that a directory is a special file in a file system, they provide mapping from this human readable text name to internal file IDs or file identifiers. Okay. And all those actual information required by the file system to management those files are called metadata. Okay. So other than the content the itself, the other necessary information for file system to properly manage those files are referred as metadata. Okay. Here is a conventional file system in most single host file system. Okay. Usually they are partitioned or layered by these modules. Okay. Underline the button is there is the physical device module. Okay. They handle the physical storage most of the time are disks. Okay, so the physical disk I/O and the buffering mechanism are handled by this device module. Okay, and on top device module there will be a block module. Okay, it handles how to access or allocate the disk blocks. Okay, I mean. A low disk in general will be partitioned into blocks, okay, and which block will be assigned to which particular file, and so on. This kind of information are maintained or managed by this block module, okay. And on top of that, will be a file access module. Okay, so whenever a request to access content of the file or its associated attributes, this read or write operation, they need to be enforced by this file access module to confirm that the access is legal and so on. So and on top of that is the access control module. Okay, there will be the operation need to be checked before pass through this file access module. Okay, so file access module support this operation of the read or write operation, and here is access control module doing the verification for the request operations. And on top of that is the file module. Okay, they will map this file ID to the particular disk files. Okay, and then the top is level, it will be the directory module. Okay, you can use the string name or human readable text name to map file name into physical file IDs, and then you use this ID in the file module to locate the address of a particular files. Okay, in the storage. Okay, and so most file systems they use this layered structure, and the functionality of file system will be partitioned into these 6 layers. Okay, and the API will be something like this. Okay, for most modern file systems, they in general support sequential access mode. That means whenever you access a file, you start it from the beginning and then one item at a time. to sequentially access the content of the files until the end. Okay, so that's the most general access pattern. Okay, so the API usually will be support this kind of access pattern, for most of file system right now. So, and before to access to any real data, usually we need to find out the address of the file, the physical ID or physical location of the file. Okay. So the file system usually use open with a name mapping. We give a string name with the access mode. And then the file system try to locate, map this file, and locate the file, and return a handler. Okay. The meaning here, the handler depends on the implementation of the file system, but in general, it's just a sequence of bytes, okay, usually something like that, and contain the necessary information for the subsequent access for the particular file. Okay. And the create is similar to open. The only difference is the name here is for open usually we try to access a file which already exists. For create means you try to create a new file. Okay, so only difference is that, but the result is the same. After create or open successfully, they will return and handler, and then subsequent operation will use this handler to refer to those opened file. Okay, and for read write, you use the handler instead of file name, and then associate with the buffer and the size. Okay. Remember here, most of the API, modern API, they support sequential access. So internally, after this open or create, the server, the file system will maintain and position for this particular files. So subsequent access, you don't need to specify the starting position of the access. You only specify the size, okay, how many bytes or how many items you try to access for this particular operation. Okay, and after this access, the position will automatically update according to this size. Okay, and if you like to change the access position, then this seek operation will be used. Okay, so the offset means the next operation you try to start it from this particular location. So instead of the originally access position. Okay, so you instead of sequential access, you like to change the access position. Then you use this seek, okay, before doing the actual rewrite. Okay. The link usually used to create a secondary name or alias of the originally existed file. For example, if you will have a file, it's name1, and you try to give this file another name, okay, then you use this API, it create new entry in the proper directory with this second name, name2. Okay, so the name1 and name2, they are paste name here. Okay, unlinked means you remove an entry from this name from the directory. Okay, so unlinked will not actually or will not delete the file. Okay, you only remove the entry associated in the directory. And get attribute will let you retrieve the metadata, okay, or file attributes. Okay. And close means after this operation for a particular file finished, then you use close to tell operating system or tell the file system that this handler is not necessary, not used. Okay, so the file system will reclaim the resource associated with this handler. Okay. Usually, each handler is associated with a data structure, the content, or those necessary information for the file access. Okay. These are the conventional file system, okay, and the APIs and their layers, okay, and functionality. Here, for a distributed file system, okay, in general, we like this. The functionality will be similar or identical to the conventional file system, okay. But now the file, instead of store in your local disk, it may store in a remote system or remote host. Okay, so they have some important or basic requirement. Okay, when you try to implement or design a distributed file system. Okay, the first is transparency. Okay, the reason for transparency is similar to the distributed system itself. Okay, so you like to present a single image view to the users and applications. Okay, so again, it's very similar to the transparency requirement for general distributed system. Access transparency. Okay, client program, they don't need to be aware about the location of files. Okay, so they can always use the same API to access files. If the file, no matter they are local or remote files. Okay, so that's the access transparency. Okay, and location transparency usually means that they can see an uniform file name space. Okay, so you can use the same file name and this file name. The system will automatically do this mapping to use this globally unique file name to find out the location of a particular file. Okay, so and they don't need to stick in a particular host and so on. Okay, so file may be relocated without changing their names. Okay, so that's the meaning of location transparency. So programs only use the same name without knowing their what's the real location of a particular file. Okay. During the programming, when you try to run your program, you don't need to know for the file in the long term the storage file will be in which particular host and so on. And this mobility transparency is a little bit new because in the general distribution we did not talking about this. Okay, but in distributed file system usually we would like this transparency. That means that both client program and administration configuration in client nodes, client host, they don't need to be changed when the file was relocated. Okay, it's similar. It's very similar to this transparency. Okay, but has more emphasis in here in this reconfiguration and relocation. Okay, without any knowledge or any modification for client side. Okay, that means once the configuration for the file system has been done, all the client hosts they don't need to be aware any long-term change of the file, physical file location and so on. Okay, their configuration or their algorithm are still valid. That's the meaning of this mobility transparency. Next is performance transparency. That means the performance of this client program to access a particular file will not be affected when the workload are varied, okay, within a small range. Okay, that means here is that if the client whenever they try to access a remote file in this distributed file system, if the workload did not vary too much, then they will always get a similar performance. Okay, that's this mean. Okay, and then if the workload changed out of this range, then we are talking about scaling performance transparency. That means the DFS can support we call it semi-linear adjustment. Okay, so the performance will be almost linear to the workload. And here the small range usually means within 5% of the variance. And here it means more than 10% or whatever. Okay, that means if the workload increase 10%, then the performance will downgrade about 10%, and maybe a little bit more. So, for example, 11 or 12%, it's still acceptable. So here we mean this semi-linear. It means that okay. So it's almost proportional to the workload and the network size. Okay, and these are scaling transparency. Okay. Besides this transparency requirement here, okay, and then the next requirement for design a distributed function is that if the file, because the purpose for this file, especially for distribution, usually is for sharing. Okay. When you create a file, you like to be shared by other applications and other users. Okay, so the nature for sharing is that then you may have concurrent file access and even concurrent file updates. Okay, so we need to be able to make sure that simultaneously access to a file, especially update. The result will not be inconsistent. Okay, so the file system need to take care about this. Okay, how to maintain the consistency of when there are multiple access or multiple update happen simultaneously. Okay, that's the design issue. And next is the file replication issue. Okay, because to support, in general, to support scaling or performance, okay, transparency, the base way or most common way is to replicate a file. Okay, so the availability of file can be increased, and the fault tolerance of the file also can be increased in such a way that when some of the storage failed, that the file is still accessible and so on. Okay, so most distributed file systems, they will support some form of replication. Okay, a file may have several copies stored at different locations. Okay, and so by using replication, we can support scalability and provide more fault tolerance. Okay, but this replicated multi-copy consistency among these multi-copies become very important. Okay, it's like a cage. Okay, multi-copy replication. Okay, you have multi-copy. So how to maintain the consistency of those copies become an important issue. And the next is the hardware and operating system heterogeneity. Okay, because the file system, the underlying hardware and the native operation may be different. However, the file system can on top of those different hardware and operating system, and then they all support the same API. Okay, so the client program can always use this same application interface to contact the file server and so on. Okay. So the API should be defined so the client and server software can be implemented on top different operating systems and different computer hardware. And also, this requirement usually is very important if we try to provide openness or interoperability of these systems. Okay. The next issue is fault tolerance. Okay, because the nature for a distribution is that you try to have more availability. So some resource become unavailable. The operation is still available. Okay, so in file system, that means those files are still available, can be accessed when some failure happens. Okay, and the next will be the file sharing semantics. Depends on the implementation or the distribution. Different kind of access semantic may be supported. Okay, in general, most of the modern file systems they support these 4 semantics. One of them, okay, most systems they design issue. This is the design choice. Okay, the first one is we call it one copy update semantics. It's Unix-like semantics, or sometimes it is referred to as Unix semantics. Okay, because the Unix in the Unix file system it's one copy update. Okay, that means that the update is immediately visible to all the applications. Okay, and the next is session update semantics. Okay, and this it is supposed by the Android file system first. Okay, so we were talking about that later. Okay, the meaning is that the reason we call it session update semantic, that means the consistency only enforced when in the session level. That means when you open the file, the update only in the local. Okay, until the session closed, the file closed, then those updates will be reflected, will become visible to other applications. Okay, so this update is not by on the operation per operation. Okay, this one copy update usually means every update operation will be immediately become visible to the other system, other programs. But here, session update means the update only become visible to other applications when the file is closed. Okay. Before the file closed, those updates during this session of this open to close session will only visible to that particular application. It's not visible to outside the application. Okay. Only after close, then those updates during this particular session will become visible to other applications. So that's the semantic provided by this Android file system. Okay. And the next one is we call it append only update, or sometimes they call it write once update or write once semantics. Okay, the example is Hadoop distributed file system. Okay, that means you cannot make any change once the data is written to become permanent. Okay, so sometimes we call it write once. Okay. However, you can append the new content in the end of file. Okay, you can always append in there. Okay, but after that, you cannot make any changes. Okay, so it's append only update. So only append. Now, this kind of update can be allowed. You cannot update those already existing content. Okay. So the purpose is that once you make the reason to use this semantic is that most time this Hadoop distributed system they used to log some information such that once they are created, you like those behavior will become unchangeable. Okay, so anything the behavior of this file access will always become traceable. You cannot undo or erase your update. Okay, every update will be become permanent. Okay, and then last semantic we call it copy on write update semantics. That means whenever you try to update something, then we will automatically create a new version, new file for that. So it's very similar to this DriveWise, okay, but it did not support append, okay. So whenever you try to make any change to the original existed, a new file will be created. So the original version will still there, and then you create a new version with those updates. This we call it copy or write update semantics. Okay. This, in general, some of the file systems they support this, and with a special support for this. Okay, so it can allow you to create a file have this particular property. Okay, and usually these are used to maintain some important configuration file or such that different versions, different applications, they may use different versions of the same files because they depend. Okay, and so on. And next, security and efficiency. Okay, we will not discuss security because there's other courses that they are talking about how security will be handled. But of course, it's an important issue for anything, any system. Okay? And efficiency here is that usually we would require that the performance of a distributed file system will be compatible to those conventional file systems. Okay? So whenever you use the remote distributed file system, the implementation, or you try to match with this conventional file system. So when you access the remote file, you try to have a good implementation such that the remote file access, the performance, the latency to access the remote file will be very similar to the latency to access your local file. Okay. Of course, to achieve this, usually it was done by client cache or whatever, similar, something like that. Okay, to achieve this. Okay. Now, after we have this requirement, okay, transparency, concurrent update, replication, right, and so on, then the first thing we need to discuss is how to name a file in the distributed file system. Okay, and usually we would like this to support access transparent, okay, and the location transparent, especially. You would like that the name, high-level name used by user and application will be independent to the location. Okay, and so usually we will need to have a mapping mechanism between this high-level logic name and the physical file locations. Okay, so a transparent DFS usually hide the file location in such a way that location transparency is the basic requirement. The name will not reveal the physical location. Okay, and another transparency, or another property we call it location independent. They will more specific require that file name should not be changed when the file's physical storage can change. Because location transparency may sometimes it can be implemented in such a way that the name can be changed whenever you move the file from one location to another. The file name need to be changed. It's still location transparent because the name itself did not contain the location information. Okay? As long as the file name did not reveal the physical location, then it is called location transparent. But location independent emphasizes that the file name will never be changed, even its physical location changes. Okay, so most systems, this naming mechanism will not only require location transparent, we also hope that the implementation or the design can support location independence. So we can separate the naming hierarchy from the storage device hierarchy. Okay? most DFS they use this three kind of naming mechanism. First one is mount remote directory to local directory. It's like NFS network file system they use, or Microsoft's file system. They all use this mechanism. Okay? It gives the appearance of the coherent local directory tree. Okay? So each client host maintains its own local directory, and the remote file servers they will mount those exported subdirectory into its local directory. Okay, and so by using this, they can support this access transparent. Okay. And the second way is that you use this host name plus local file name. Okay, to guarantee a system-wide unique name. Some example is okay, Apollo, that's the old system. Okay. And last one is total integration of component file system. That means the name itself, the system support a single global name server. Okay, so the file location or file hierarchy is irrelevant to this naming structure. Okay. So most systems they use either one of these. Okay. Of course, this last one is most difficult. So, but if you use a centralized implementation, then this one is not too difficult to implement. Okay, but the central server, the central global name server, become sometimes become the single point of failure or bottleneck, and so on. Okay, so but anyway, this approach is much better for transparent okay, support a better transparency. Okay. The first one is mounting remote directory. So this is a typical example. Okay, so if assume we have a file server here, okay, and you may have a two client host, and every client host they can mount this exported subdirectory into its own file directory structure. Okay. But they may mount it in different way. Okay, so for example, client A may mount this Steam subdirectory into here, but named it as VU subdirectory. Okay, under this remote stage VU. And for client B, the same subdirectory may be mounted into this stage work, stage B, and so on. Okay, so when you run the same application or the same user, but you use different kind of machine, they may see the same file by different names. Okay, so this kind of system usually only support access transparent. They did not support location transparent. Okay. To support location transparent, you need to ask every client host they mount this same subdirectory into same way. Okay. So usually, if those client hosts are managed by the same manager team, then it's possible you can do that. Okay. If this client host did not belong to the same domain, management domain, then they may different the name for the same file in the server may be different. Okay. To access this file in DFS, usually have this remote service model and data cache model, and then this data cache is we talked about before. Is this upload download model? Okay. Here we just refresh memory. Okay, we talking about this before. Okay, the remote service model means the file action or real access are performed in server side. Okay, and it's usually used for those client machines with only small memory or without local disk. Okay, and usually if those access involve a lot of write operations, then this model will be much preferred. Okay. But for data caching model, or sometimes we call it upload, download model, that means whenever you open the file, you move the copy into your local, and then doing the local access until close. Okay. Then the server is only contact when it is necessary. Okay. And it can reduce the network traffic and the server load. The advantage is that, but however, by doing this, the coherence or consistency problem need to be handled with scale. Okay. Usually, this kind of mechanism support more scalability, okay, and the performance will be much better than this. But they need to take care about this replication consistency or cache consistency problem. Okay. To increase the performance or support to support this, okay, to make the performance of a device become compatible to its conventional counterpart, usually we need to use some kind of cache, okay, and because a client machine, if the file is stored in the remote server, then there are 3 possible locations you can install a cache. Okay, for example, you can install cache in the server's memory. Okay, you can use the cache in client-side memory, or if client has a disk, then you can have a cache in client's disk also. So usually you have this at least 3 possible locations to install caches. Okay. Of course, the system may install 3 caches in this all 3 locations in the same time. It's possible. Okay. A cache in the server memory usually means that you can allow some frequently used file will be cached in server memory in such a way that when any client try to access, then it will get a fast response because the server did not need to get the content from the disk. Okay? So most server remote implementation, the distributed file servers in the server-side implementation, they will use this server memory as cache, especially cache for those frequently used directories. Okay, because to look up a directory, or especially for those system directories, okay, library or system directory, you can cache then those information in memory. So because most clients they need to access that before access to the real files. Okay. So some important directory information will be always cached in server's memory, okay, to provide fast response. And also, if the system supports Unix semantics, then a client server memory cache will become much easy to support, okay, because any update will immediately become visible, okay, because the update always go to the server memory first, okay, instead of to the disk. Okay. So not only support the efficient performance, but also support is update consistency. Okay. The second possible way is in client-side memory. Okay. So you can cache, you get a better performance speed up if the file, the system, especially for sequential access of the files. Okay. We can anticipate this. So when you open a block, for example, because the disk operation is in a block level, okay. So whenever you access a byte, okay, the disk will return a block contain a byte, right? And if we cache the whole block in the memory, then subsequent access may still already in the memory. Okay. So this client memory usually cache will associated with the buffer management. Okay, so of the blocks. Okay, so and so the performance will be generally much better. Okay, than without this memory cache. Especially if the update are very rare. You open the file only for read, then this content cached in memory, or even use the read ahead cache will support a better performance. Okay. And the last possible is a cache in client-side disk. Okay. If the disk client has a disk, and those disks can be able to be used to cache larger files or and so on. Okay. So whenever you open a file, a lot of file blocks can be pre-read into its disk. Okay. When the network is not too busy, then they can do this kind of operation. Okay, before you actually read those blocks. Okay, and so on. Okay. And this we call client disk. Okay. And it's good when the local use. Most of the time, you use the local files, local disk instead of. Okay, so especially in Android file system, they use the whole file cache. They move the whole file into its local disk, okay? And then subsequent access are all in the local disk instead of go to the server. And also, this kind of cache can prevent, or not prevent, that can make the file still become available when even the server crashes. Okay, during this access. Okay, so let's the relationship of this. Okay, a client program running in client's memory. If the client side has a disk, and server program running in server memory and server disk. So the original data is stored in server's disk. Okay, but you can cache in memory, server's memory, or cache in disk, client's disk, or even in client's memory. Okay, or you can cache this in 3 positions as well. Okay, depends on the implementation. Okay, and any cache, they will make the system become much efficient a little bit. Okay, but the management, if you have a more layer of the caches, then the management issue will become heavier. Okay. With cache, then we need to talking about how to make cache update. Okay. And this we call cache update policies. Okay. Cache usually we can use when the update, especially for the real access, you don't need to worry about this. Okay, only when the update it happens. Okay, so most commonly we have a write through or delayed write. These two update policies. Okay, write through means the data will be write to the server's disk as soon as possible, and each write operation need to be propagated to disk server's disk before this write operation be considered as complete. Thing. So this write operation will not return until its data return to the server's disk. Yeah. It provides reliability, but the performance in general will be worse. Okay, will become poor. Okay. Because all the write need to go through the disk server's disk. So most modern systems they use some kind of delayed write scheme. Okay. So the data usually write in the client's cache first, and then we propagate back to the server later. Okay. The advantage for this step, if the client program makes several write to the same block of the data, then those write will be accumulated as a single write operation whenever this write propagate back to the server. Okay, so you can reduce some network traffic. Okay, that's all. So this overwritten in this cache line or cache blocks, they can be override or they can accumulate together until so the network traffic will be reduced. Okay. Of course, the reliability will become less than this write through. Okay. Okay, let's take a short break.你们大概什么时候会改完？你们大概什么时候会改完？期中考，第二次的考试。
看我已经改完。
你已经改完？
我的部分已经改完了。
Okay.
他们那个嘉音刚才在改。
OK， 好，看下礼拜能不能改完。
好，我们今天。我把那个就是科学。
OK。
这个，因为我在想我们的 highlight 主要是在讲 GDP 啊。
对啊。
然后它里面就隐私保护的东西，但是我们的系统没有，就是我们 highlight 里面没有讲到 SSI 相关的东西。那我在想说要把 SSI 这一点也加进去。加进
可以啊，可以啊，因为我们 support SSI 的大部分的东西嘛，对。那我们不 support 那个，就是因为我们希望让政府可以 audit 嘛，这样。对，可以啊，可以啊，就把那块加进去。
然后下面是那个产业之应用。对。从这边开始。
可以啊，就这种这个。
好，到时候再去做一点修正。然后那个我们那个老师有传那个叫什么 color 的那个。
对。
paper color
那个我们就他不是有个链接嘛，就上去把它说我们不要嘛。
好，那个部分我已经用了。然后它好像还有2个点要点，就是好像确认整个 paper 的东西。
那就先进去看看嘛。
好。
他说已经完了，都没有问题，就把它确认掉。
那但是我发现我已经发现一个问题，就 auto statement 那边我不小心放到 equal volume 那边的东西。对，所以那个学习，对我是直接寄信过去还是？
对，就直接改掉就好。
好，那我到时候，是可以直接改掉。
他能不能直接改还是怎么样？
我到时候先看一下，
对啊。
然后不行的话我就直接寄信到那个。好，那应该就有是然后我们今天等一下会去在那里新店，然后再去拿那个转接头，会顺便买一个转接头回来，因为我们觉得原价我可能应该不会送。
在什么？
电脑，就那台那个4090G 的电
脑。他为什么不送？
原价的价格很硬，它不会有那种折扣的一些优惠，它连那刷卡都不行，它全部都只能付现。
还有这种公司啊？
就很让人意外。但它的价格好像又相对比其他的，就它的东西比较齐全，我们是这样觉得。所以我们到时候买完之后是要直接拿过来，还是？
不是啊，你那个现在是那个小队不是说他那个钱是系上同意了是吧？还是怎么样？
系上同意。是好像听那个小队讲是主任懂那个。对。OK。对他就到时候可能那个我不知道是不是主任懂那个。
你要问他一下那个账他怎么开啊？
就是他就跟学校报账的流程一样。我问过。大概是这样。那应该就没。因为
主任有一些私房钱啊，就是系上有一些钱给他自由用。对啊。另外就是说，你那个 Digital Health 那篇，不是被就你把那个相关的 information review 的意见啊，还有那个原稿那篇寄给陈老师就让他看他说后续看他想要改，他转投到哪里寄给陈世伟，然后另外跟他讲说，就是那个信户的那个论文如果要写的话，就我们现在这边没有空，也请他那边处理。
该是他，我猜他应该已经开始处理了。感觉那个蔡主任他想要退休，不想要退休，他应该要尽快把它弄出来了。对，因为那时候他就是因为蔡主任要退休，所以他才说要把那一边接手过去。那现在这边的话，我还没跟那个陈世伟老师讲，我到时候去跟他讲一下。
对啊，因为这边就是人家有一些意见嘛，他如果改一改，然后就看他要投哪里，再去投。
好，那我就直接转发给他。
对，然后给陈老师，因为那个他不需要重写嘛，他只要把那些地方改一改，然后他又把它改啊。Okay, we are back. So for the
delayed write, the disadvantage is that you have some reliability issue, okay, because those unwritten data maybe get lost when client machine crashes, okay, if they still in the client's cache, okay. So some kind of inconsistent may occur. Okay. So in general, this delayed write, to avoid or to reduce this inconsistency or to enhance readability, usually we have these three variations. First, we call it write-on ejection. That means because cache usually is limited size, so the system need to incorporate some kind of cache replacement mechanism there. So whenever a cache line become bigger, need to be evacuated, then those content will be right back to the server. So that's the mechanism used. So whenever cache, so you delay this write until the cache line need to be evacuated. Okay. The second variation is periodically you just write back all these cache, okay. And that one is write on close, especially for the session semantic. When the file closed, then all the cache write block will be written back to the server. Okay. So most systems they use overlay. Okay. Some of most modern systems, because this mechanism did not conflict each other. Okay. You can incorporate overlay. Okay. The reason for that is periodical means you try to reduce the timing for this possible inconsistency. So you set a periodic timer whenever if anything in local, then you just write back. And for the write on ejection, of course, whenever you need to replace some block, you always need to make sure that those evacuated block need to be written back. And the last one is so this first one and last one is necessary. You always need to do that. Okay. And the second one is you can just add this periodically mechanism, so it can reduce the timing for possible inconsistency. Okay. And to make sure this cache, okay, because when you have cache, then it's possible the same data will be cached in several clients, right? And any client, especially by using delayed write, okay, then when the client's write propagate back to the server, then those other clients' cache may need to be re-verified, okay, revalidated, okay, or maybe need to be invalidated, okay, and so on. So we need to have these cache validation policies, okay, to be enforced. So multiple caches, their content, and need when the client program access its local cache, you always access the right the valid ones, okay. And in this validation policy, or usually we will have these two approaches. The first one is client initiated, that means this validation process initiated by the client itself. Okay. So a client may initiate a validity check with the servers. Okay. And usually in these three possible variations, one is check before every access if the system need to provide this unique semantics, okay, because otherwise you don't know you get the right content or not, okay. So before every access you need to check, okay, your local copy is still valid or not. And second one is periodically checking, okay. Use a predefined time interval, so periodically you go to see your current copy is still valid or not. Okay. If it's not valid, then you get a new one. Okay. And then last one is you check the validation whenever you try to open a file. Okay. It's usually supported in session semantics. Okay. And the validation usually based on this timestamp or version numbers. Okay. It depends on the implementation. Some systems use version number, so whenever you have an update in the server, so update the server will keep increase this version number. It's just a logical clock. Okay, whenever you have a new update, then you increase your version number. So the other caches they can just use this number to validate. So it's current, is the right version or not. Okay, and so on. Or you use the timestamps. Okay, it's similar. Okay. And the next approach is server initiated approach. That means the server record the information about those cache client. Okay, usually for every client cache, server need to record. There's one client in there. They have a cache for some particular blocks and so on. So whenever you receive an update for a particular data block, then the server will try to invalidate those inconsistent caches. Okay. So these are server initiated approaches. Okay. So server detect potential inconsistent, you react. Okay. And this potential will happen when a file open for conflict access from different clients. Okay. Or a file is closed with multiplication. Okay. Then the server will initiate validation. So the validation policy, okay, it depends on how the system implement. Okay. To implement server initiated project, then the server need to maintain information for client side. Okay. The server need to know there's which client has which cache, okay, and so on. But for client initiated cache approach, the server don't need to record this information. It's become client's responsibility to make sure it get the right version, right to use, okay, and so on. So the philosophy of these two approaches are different, okay, are different. Replication is a way to increase the availability for distributed file systems. Okay, and replication and cache, although they are all a means of some kind of increase the number of copies of the same data, right? But the purpose are a little bit different. Okay, so here we will say something about the difference, okay, replication and cache. Usually, a replication, or usually we call it a replica, is a copy in the server side disk. Okay, that means you will fire. You will fire two replication. Two replica. That means this file will store in two different server disks. Okay. So a replica usually means there's a copy in the server disk, and cache usually is a copy of a replica. Okay. And a cache usually depends on file access pattern. Whenever you create a cache in a client or create a cache in somewhere, usually it means this particular portion of the file is frequently used recently. So you create. So it depends on the access pattern. Okay. But for the replication, usually it depends on the overall availability and the overall performance requirement. So the creation reason are quite different. Okay. And replication usually is persistent. And why do they know? Why they know means inside this file system, okay, especially the global naming server, they will know this replication, the existence of the replications. But the cache usually is not known by these name servers. Okay, they only known by the client or the server side. Okay, and the existence of a cache depends on the presence of a replica. So cache usually associated with a particular replication, okay, not the whole file. Okay, the cache is also when the user program first open the file, the name server will try to map this open to a particular replication, and then after that, those related caches will associate with that particular replica. Okay, and so on. So that's the, and they need to be periodically be validated with the particular replica. Okay. So that's the difference between this replication and cache. Okay. The purpose are different. The creation time, the reason to create are also different. Okay. The transparent also for the replication is, of course, we said it before. So a replicated file can be viewed as a single logical file to users. So most of the time the user, they don't need to know explicitly know a file as a replicas. They just see as a single image. But in reality, the file system may maintain several copies in different disks. Okay. So the issue for replication transparency is that was naming for the replicas, the physical name for the replicas. Okay, because every replica is a disk copy, right? So they have a physical underlying low-level file IDs. Okay, the high level they may use the same file name, but this file name will map to several physical file IDs. Okay, and this will be managed by the name servers. Okay, to do so. And the replication controller means how many copies and how to enforce those copies are consistent. That's the replication control. Okay. So naming scheme must map a replicated file name to a particular replica. So the existence of replica will be invisible to high level. Okay. So from the user's point of view, we only know this high level name. Okay. So when you present this high level name to the file server, when you, for example, you try to open the file, and this open operation will map to a particular physical files. Okay. And so the replicas, they need to be distinguished from one another by the label names. And the replication control include how many copies need to be maintained and in which locations. And this can be explicitly specified by user or implicitly specified according to the DFS requirements. Okay. For example, some system may provide this explicit replication. User can specify when they create a file, they specify how many copies they need to be created. Okay. For example, in DFS, in Hadoop file system, okay, they support this explicit replication. Of course, they have a default number of replications. Okay, if you don't specify, they use default, but user can specify explicitly. And the second possible is implicit. The DFS they automatically adjust depends on its configuration. Okay, and so on. To make multiple replication, when update a file with multiple replicas, then we need to make sure their content are consistent. Okay, so the system, the application file you need to have a multiple copy update policy to enforce the consistency. Some systems use this read-only replication. That means only those immutable files, read-only files, can be replicated, can have multiple copies. Okay, so the reason to use this operation, they don't need to take care of this multiple copy for write updates. If a file can be updated, then they cannot have replication. Okay. Only those files they are read-only, they can have replication. Okay. So by using this approach, you don't need to worry about the update, the problem for the updates, because for writable files, they always have only one copy. Okay. Of course, this kind of approach have its limitations. Okay, so the second one was proposed. We call it 3-1-0 protocol. Okay. That means when you may have an copy in the system, okay, but whenever you try to read content, you attach to any copy is enough. Okay, you can get content from anyone. But whenever you try to write, this write update need to be propagated to all the copies. Okay, and until all the copy be consistent, then this write becomes successful. Okay. So this we call read one by all. Okay. So read operation performed by any copy of the file. The write operation must be performed to all the copies. Okay. So implement this, we need to have some kind of locking mechanism to ensure this write operation can successfully apply to all the copies. Okay. And to use this, then this Unix semantics can be supported. Yeah, this Unix update semantics can be supported, because whenever you try to write, everybody after all the copy are updated, then this write return. So that means the result of a particular update become visible to all the programs. And this approach usually can achieve high efficiency when this read-write ratio is large. For example, most of the time, this file, the read operation has 90%, write operation only less than 10%. Then this operation will become acceptable, because the overall performance will become acceptable. Okay. And the disadvantage for this one is that if any of the copy crashed, then this write operation become unavailable. Okay, so later there's another modification of the adjustment for this protocol. We call it available copy protocol. That means it's similar to this read one by all, but the write only write to those available copies. If some copy crashed, then you don't care about that. Okay, only those failed server, when they recover, they need to bring itself to the newest version, and then this server can be joined, become available. Okay, so the number of copies is dynamically changed. Okay, when a server crashed, then this n become n-1, for example. Okay, so the update are only performed on those available one, still operational one. So this kind of approach, then it allows the system, some server crash, and they still provide write operations and read operations. Of course, then the system needs to have a way to make sure that when the server crash recovered, okay, if there's a copy some replica of a particular file. This server, during this recovery process, okay, this file server need to find out the current version of those replications, and then get those new versions until all its files, maintained files, or maintained copies of the files are in the newest one. Then this server can rejoin to become available one, okay. And then they can provide service to the read and write. Okay. The next approach is we call it primary copy. This read, write all or available copy, they all need to enforce that the write operation need to propagate to all the copies, right? Or either they are operational of all the copies. Okay. So the write operation is very poorly. The performance or the latency for the write usually is very low. Okay. So to reduce or to remove this limitation, this primary copy approach was proposed. So there's one particular copy is designated as a primary copy. Okay. So read, again, you can perform using any copies. But whenever you write, you only write to this primary copy performed in the program first. And secondary copies are then updated later. Okay. Of course, there's a duration in there. Okay. And the consistent semantic proposal by this kind of update policy will depend on when the secondary copy are updated. Okay. If the system try to support unique semantic, then the secondary copy need to be updated by primary copy as soon as possible. Okay. And also, so some kind of plugin need to be used to carry out this update. Okay. So in practice, how this work in this way. So when we try to use the write, you perform in the primary copy. In the meantime, you will lock all the secondary copies. Let this copy become unreadable. Okay. Until their content they become newest one, then they become readable. Okay, then acceptable again. Okay, and because this propagation of the new copy to the secondaries, they can be propagated one at a time or by the primary. Okay? And the speed or the latency is controlled by the primary copy. Right? Okay. But before the primary copy, they propagate to those secondaries, they need to do something. Usually, the best practice is that when you perform this, and you, in the meantime, you set those secondary copies become inaccessible. So when primary copy, they make the one, for example, the secondary copy become after today, then the status of this one become accessible. So the read operation then can be performed. Okay, so it depends on this propagation of the updates. Okay, and the number of readable copies will be dynamic increased until everybody become available. Okay, so you just delay this you make some of the copy become unreadable during this transition. Okay. So if a system need to support, this is for the unique semantic. If a system support other kind of semantic, then the write operation they can return whenever the primary copy become updated. Okay. Then they may be able to return. Okay. And secondary copy then can be update in the background, okay, and so on. Okay. But this depends on how the semantics the fire system support. Okay. For example, if a system support this append only update, then the time, the latency for the primary to the secondary can be very low, because and those secondary, they are still readable. Only those newly appended content cannot be accessed, but original data is still available, can be accessed. Okay. So it depends on the semantic supported. Okay. So this is approach that try to increase the performance of the right operations. Okay. The next update policy we call quorum-based protocols. Okay. These are first proposed in 1979, very early, okay, by this Gifford scholar. A simple protocol we call quorum consensus protocol. They can handle crash and network partition and whatever, okay. And allow the available disks or available servers, they can still perform some read or write operations, okay. And the algorithm is something like that, okay. If a file has n copies, okay, then whenever you try to read, you always contact at least R replicas, okay, and this R is a preset parameters, and this we call it recallers, okay. You get you are able to communicate with R copies. Then and use this latest version of these R copies. So different copies, their version may be different, okay. But as long as you have R copies contact, and you find out, you use the latest version one, and then you read the content of that one, okay. Use that one as your latest one content to read. And for the write operation, you need to contact at least W replicas, and this W will be a strike colon, okay. And this W replica need to be locked, okay. And then you can perform the update to these W copies, okay. As long as this R and W, the value of R is satisfied the following condition: R plus W is greater than N, and 2W is also greater than N. And the reason for these two constraints is that every read will make sure that they always get the data strike, okay? Because if R plus W greater than N, that means whenever you try to read this recorder, these R copies, they will have at least one of them came from the last write, okay? Because the write need to be write to W copies, okay? So you can always get the data right, get the result. And if 2W greater than N, that means the write, every write operation is always performed on top of the latest write, okay? Okay? So this constraint enforces that if you set the system have n copies of file, and you choose proper R and W, and the value of W you can choose this depends on the frequency of the file to be accessed by read or by write, okay. For example, if the operation frequency of read and write is 3 to 1, for example, then that means you probably should set the value of R become 1/3 of W, okay. Then the performance will be much reasonable, okay, and so on. So something like that. Okay. So it depends on the frequency of the access read-write access to this particular file, then you choose different proper read column value and the write column values. Okay? And this protocol, the actual practice is something like it. Whenever we try to do a read, we retrieve a read column, okay, R copies of the file. Of this R copy retrieved, you select the copy with the latest version, and then use the content. Okay, you perform the read operation on these selected copies. So before you doing actual read, you contact these R copies and get the permission, get their version numbers. Okay, and then after that you choose the biggest one to read. Okay. Then you always read the latest write. And again, to write, we retrieve a write column, W copies, and you get their largest version number. And then you use this version number, you increase at least by 1, okay, and then write a new value and the reversion one to all the W copies of these write columns. Okay. Of course, this column, the association of this column, okay, maybe the granularity may be associated in the block level or in the whole file level. Depends on how you implement this. Okay. In general, if you try to make this concurrent update become much efficient, then you should let this become in the block level. Okay. So whenever you try to access a particular block, then you perform this read or write only on that particular block. Okay. So every block will have its own version number. Okay. Of course, the whole file may have the same R and W values, but different block will have its own version number. Okay. Depends on which the update frequency of that particular block and so on. Okay. So this column consensus protocol can be worked, depends on the layer frequency. You can adjust this, okay, R and W values. Here is an example. If a file has 8 copies, then you can, if you choose this value, that means they have at least 1. Whenever you try to read, you can always find out this read will contain the last write. One of the copy will be in the last write. Okay, and if the RW is in 2 and 7, then also they will certify. Okay, but the reason for different setting of this R and W, it usually depends on the frequency, the operational frequency of read operation and write operation. Okay. For this kind of setting, usually means the write frequency is much higher than this kind of setting. The figure A and figure B, okay, the reason to set a value like this usually means the frequency of the write in this one is much higher than the frequency in here. Then you should choose the value of W become a little bit smaller, okay, and you increase the value of the R, okay, because the frequency of these two operations are very similar. Okay, and this one they have a big difference. Then you choose something like this. Okay, so it depends on the frequency of read and write. Okay. If they are very close, then you choose R and W in very close value. If their difference are big, then you can use a smaller R and bigger W. Okay. This column consensus protocol actually is a very generic policies, because the read1.0 protocol is just a special case of this, right? Read1.0 means R is 1 and W is N, right? So this become the special case of this column consensus. Okay. And there's another way we call majority consensus protocol. That means you set R and W become the same value. Okay, here I have a new version. Okay, so if you download a new one, then this should be fixed. Okay, this one is then actually should be set to the ceiling of n over 2 plus 1. Okay, it will be much proper. Okay. And for this protocol, usually means the read-write operation ratio is very near to 1. Okay, that means use majority consensus. Okay. Another variation is that consensus with weighted voting. Okay. Because in general, every replica, the importance of the replica may be different because different server may have different capability. Okay, some server may be faster than the others. Okay, and so on. So it's possible in practice, different replica may be assigned to different boards, depends on their capability. If a more capable server, you can give the weight a little bit higher. Okay. So the read column become R bolts instead of R copies. Okay. And write column become W bolts. Okay. And the total number of bolts for these replicas, these M replicas, if it's V, then the two constraints become R plus W need to greater than total bolts, and 2W need to greater than bolts. So to accumulate a recorder means you accumulate R bolts. You can communicate with some copies until those copies, their total bolts is greater than R. Then this set of replicas will contain the latest version of the that's right. Again, whenever you try to do the update, you contact some copies and accumulate their bolts. Okay, if total bolts accumulated is greater than or equal to W, then it means these copies, at least they have one copy is the last write, belong to the last write. Then you can make your update into the copies and then propagate the result to the other copies. Okay, and make sure those copies, those W bolts associated copies, they will all become the new latest one. Okay, and so on. So instead of every copy has one bolt, right? They can have different bolt, depends on their capability. They can assign different bolts, and you make this constraint become this using the bolt number. So total bolt is W is V, then R plus W need to greater than V, and 2W need to greater than V. Then this can guarantee that read always read the latest copy, write always on top the latest copy, right? Okay. Any difference? Okay. So that's this variation. Okay. And this one is the more general one, most general colon consensus protocols. So after we discuss this update policies, okay, the next issue is the servo. Remember we say something about this cache, okay? Cache, okay. We say this cache validation policy. One is client initiated, and the second one is server initiated. And we mentioned that if in the server initiated project, server need to maintain the information about clients. Okay, and for this kind of service server, the server maintain the status of its associated client. This kind of server we call it stateful service or stateful server implementation. Some file server, distributed file server, they use stateless approach. That means file server side did not maintain any information about its associated clients. Client need to maintain its own status by itself. Okay, and this we call it stateless server and stateful server. Depends on the server maintain client state information or not. Okay. So for stateless server, they don't keep any state information of client. So they treat every client request as independent. Okay. So the request always need to be self-contained. They need to contain all the necessary information for the server to operate. Okay. So each request must identify the file and the position. Okay. And so sometimes they don't need to have an express open or close. Although most stateless server they all support this. Okay. The reason for that is not to maintain the status. The reason is that you do the mapping once, okay, instead of do the mapping for every request. Okay. So whenever you try to access a particular file, you call the open and do the mapping, and then you get a handler. So the handler is kept in the client. For the server, they don't need to maintain they don't need to record the handler. Okay, but the handler will contain some information that server to access the real file become much efficient. And so, okay, so most stateless server they also support open and close. Okay. But the reason is not to record its information, but the reason is to do the mapping. So the subsequent access, they don't need to do the file mapping, name mapping for each access. Okay. A typical example for this is the network file system version 3 and earlier versions. Okay, they use this approach. Okay. And the stable server, they maintain client state information. So they don't need to. Of course, they need to have the express open, and after open, they will maintain this particular client's state. So the subsequent access for a particular client, they will know this access depends on the previous access. Okay. Their dependency can be maintained. So the result for previous access can be used for the later access. Okay. This Android file system and NFS version 4 and later, they use this approach. Okay. So here's an example to demonstrate what the stateless file server, their API and their operation sequence. Okay. If the server is a stateless server, then client need to maintain its own information about file and mode and read-write pointers position for that particular file. Okay. And not only file name, but also the file handler. Okay. But here we use file name to simplify the problem. So whenever you try to read, you need to send the starting position for this read and the size and with a buffer. So the return will from byte 0 to 99 for this particular file. The next, for example, you try to do the subsequent read for the same file. Okay, this file name and file name are maybe the same or different. Okay, then you always need to specify the starting position. So after return this, the reader pointer for the client, for this client, they will change it. The starting position, for example, for a particular file, initially starting position, the pointer is 0. After this read, then the pointer becomes 100, for example. And then next time you want to send a read request, you use this as a parameter to send the request to the server. So server just use this. Server did not need to record anything about the client. Okay, they use this parameter to access the particular file content, and then return this byte from 100 to 199 and so on. And this same file access scenario, if we use stateful implementation, then the sequence will be something like this. You open the file and the server maintain this file ID mode and return this file ID. Okay. And the next time the client uses this ID with only size, because this read-write pointer initially would set to 0 and this size, so they will always return 0 to 99, and then this pointer will become 100. So next, for the same file ID, they will return 100 to 199 bytes. Okay. So the information of this will be maintained by in the server side, okay, for stable file server. So that's the typical difference for these two different implementations. A stable server will lose those temporal state in the crash when something happens. Okay, so they need to restore those state by recovery protocol based on a dialogue with those clients. Okay, and so on. And server need to be aware if a client process crashed. Otherwise, because here server maintain this information. If an associated client crashed, then this resource need to be reclaimed. Okay, they need to do the garbage collection or whatever. So the open detection, the garbage detection, and in are needed to make sure those associated crashed client, the state information maintained by the server associated with this failed client need to be reclaimed. Okay, and so on. Otherwise, the buffer in the server will be reduced, okay, when time go by. Okay, and some environment require stable service. Sometimes it's not necessary. You can always implement the same service by stable and stateless. It's not always a design choice, because some application or some situation stable is needed. For example, when we use the server-initiated validation cache policy, then you always need to implement the server in stateful. Okay? If you try to use this policy, then you need to maintain state information for this client. Okay? And also, if you try to use file lock-it for the files maintained by the server, then we need to have stable service implementation. You cannot use stateless implementation to support this server-initiated cache validation, or to support lock-it, file lock-it. Okay. But the advantage for stateless server is that the failure and recovery become very, very easy, because you don't do anything, right? The server crash and recovery, they don't need to recover anything. They just bring up because the state memory is kept in the client. Okay, so client just do the retransmission one again and again, and eventually when server comes back, then they can continue to provide service. That's it. Okay. The penalty for using this stateless server is that the request message usually contain more, because they need to be self-contained. So the request message need to have more information than the stateful service implementation. For example, here, this stateless stateful, we don't need to have the starting position, but for the stateless, every request need to have this starting position and may need to have this file name. Okay. But for stable implementation, you only give the size. Okay, that's just a typical example. So, although the robustness is higher for stateless, but the process time for message usually a little bit longer. Okay, so we will stop here. Okay, and next week we will discuss some example of this distributed file systems. Okay?
哎，你这里面不是最新的。